Hi everyone, welcome to Harmonic Functions. This is another video presentation on complex differentiation. In this, we are going to discuss about the properties of analytic functions, harmonic functions, conjugate harmonic functions. Properties of analytic functions. Property number one, if f of z equal to u plus iv is an analytic function of z equal to x plus iy, then both u and v, that is the real and imaginary parts, satisfy Laplace equation del square phi equal to 0. That is dou square phi by dou x square plus dou square phi by dou y square equal to 0. The meaning is both real and imaginary parts u and v satisfy Laplace equation, which means real part u satisfies Laplace equation del square u equal to 0. Similarly, imaginary part v also satisfy Laplace equation del square v equal to 0. Harmonic functions. Any function of x and y which possess continuous first and second order partial derivatives and also satisfies Laplace equation is called a harmonic function. By property 1, the real and imaginary parts of an analytic function satisfy Laplace equation. Therefore, if f of z equal to u plus iv is an analytic function of z, then u and v are harmonic functions. But the conjugate is not necessarily true. That is, even if the real and imaginary parts satisfy Laplace equation, but the given function f of z equal to u plus iv need not be an analytic function. Next, conjugate harmonic function. If f of z equal to u plus iv is an analytic function of z, then u and v are harmonic functions. Such functions u and v are said to be conjugate harmonic functions. That is, u is called the conjugate harmonic function of v, and v is called the conjugate harmonic function of u. Property 2. If f of z equal to u of x comma y plus I into v of x comma y is an analytic function, then the curves u of xy equal to c1 and v of xy equal to c2, where c1 and c2 are constants, are orthogonal to each other. That is, the product of the slopes must be equal to -1. Property 3. If f of z is analytic in a region R and f dash of z equal to 0 everywhere in R, then f of z is a constant function. Property 4. Now let us prove that an analytic function with a constant real part is constant. Similarly, an analytic function with a constant imaginary part is also constant. Now let us prove that an analytic function with a constant real part is constant. Let f of z equal to u plus iv be an analytic function. Given that the real part u is constant, therefore dou u by dou x equal to 0 and dou u by dou y equal to 0 upon differentiation. Since f of z is analytic, it satisfies Cauchy-Riemann equations, that is dou u by dou x equal to dou v by dou y and dou u by dou y equal to minus dou v by dou x. Therefore, dou u by dou x equal to dou v by dou y equal to 0 and dou u by dou y equal to minus dou v by dou x equal to 0 by the above equations. On differentiation of v with respect to x and y, we get v equal to a constant because v is independent of the variables x and y. Hence, f of z equal to u plus iv is a constant function. Similarly, we can prove that an analytic function with a constant imaginary part is also constant. Property 5. Now let us prove that an analytic function with a constant modulus is constant. Let f of z equal to u plus iv be an analytic function. It is given that modulus f of z equal to constant. Therefore, rewriting this, we get root of u square plus v square equal to constant. Squaring both sides, we get u square plus v square equal to c square or c, where c is a constant function. Let it be equation number 1. Differentiating equation 1 partially with respect to x and y, we get the equations u into ux plus v into vx equal to 0 and u into uy plus v into vy equal to 0. Since f of z is analytic, it satisfies CR equations. ux equal to by and uy equal to minus vx. From the above equations, we have ux plus bvx equal to 0 and vux minus uvx equal to 0. Now solving for ux and vx, we get ux equal to 0 and vx equal to 0. By CR equations, we also get uy equal to 0 and vy equal to 0. Therefore, ux equal to uy equal to 0 implies u equal to constant on integration. Similarly, Vx equal to Vy equal to 0 implies V equal to constant upon integration. Therefore, f of z equal to u plus iv is a constant function. Property number 6. If f of z and f of z bar are analytic functions of z, let us prove that f of z is a constant function. Let f of z equal to u plus iv. Then f of z bar equal to u minus iv. Given f of z is an analytic function of z, it satisfies CR equations. Therefore, ux equal to vy and uy equal to minus vx. Also, f of z bar is analytic. Therefore, by CR equations, ux equal to minus vy and uy equal to vx. Now, by the above two equations, we get vx equal to 0 and vy equal to 0 by solving. On integration, we get v equal to a constant, since v is independent of the variables x and y. By using CR equations, ux equal to 0 and uy equal to 0. Therefore, u equal to constant on integration. Therefore, f of z equal to u plus iv is a constant function. Thank you.